Hello, I am Matt from Clover Voice. This presentation topic is on approaches to managing risk and high-level control in intelligent agents. Shall we now take a listen to NAVER Labs Europe Christopher Dance's presentation?
NAVER Labs Europe joined NAVER in 2017 and is based at the spectacular castle in the French Alps. We've been doing AI research for over 25 years, and today our research has two main areas of focus: AI for robotics, on which we work closely with NAVER Labs in Korea, and natural language search and recommendation, on which we collaborate with NAVER Search and Papago Translation. Our robotics and natural language research is increasingly dependent on GPUs in the cloud. The notion of cloud robotics has been exciting researchers for the last decade, motivated by storage, computation, and power. Cloud storage enables the sharing of huge detailed maps among a fleet of robots. Cloud computation enables brainless robots, in which complex neural network processing of sensor data and optimization of controls are offloaded to the cloud via a wireless link. In this way, a robot as small as a mouse can be as smart as its elephant-sized cousin. Brainless robots are cheaper and less power-hungry too, as they no longer need to carry a GPU and cooler. That means they can devote their precious batteries to their motors. Until recently, cloud robotics was limited by latency, but right now, 5G is making it practical. Meanwhile, for our language models to be competitive with the state-of-the-art, they now need tens of billions of parameters. That's 2 orders of magnitude more than the models we used to use for large-scale image categorization. And as we start to control robots with reinforcement learning, we often need millions of iterations to train a single agent, which can take days of GPU time. And to produce results for different benchmarks and to tune hyperparameters, we often need to run our experiments hundreds of times. We work on many topics at NAVER Labs Europe, but for today, I've chosen a sample of just 3 ongoing topics that are going to be of substantial importance in the future of AI. First is the question of how to ensure that robots behave safely and use appropriate measures of risk. Second is the question of how to get robots to perform diverse tasks. While robots are currently very good at repeating expertly planned actions in carefully controlled environments, how can we enable non-experts to get robots to perform less repetitive actions in less controlled environments? Third is the subject of language generation. Recent progress means computers can now generate text that's largely indistinguishable from human prose. But how can we ensure that such algorithms make the points that we intend and abstain from expressing all sorts of unwanted opinions? These 3 themes all involve reinforcement learning, or RL. RL is all about learning policies. Now, a policy is just a mapping from the state of the world to an action. And depending on the state of the world, an action may be good or an action may be bad. Sometimes, if a robot moves its arm to the left, it helps to pick up a box. But other times, moving its arm to the left may make it break something. So in RL, we associate a reward with each state action. And the idea is to learn a policy that maximizes the sum of rewards over time. That sum of rewards is called the return. Since 2016, RL has grown rapidly in robotics. Yet, despite this interest in RL and in safety-critical applications like drones and autonomous vehicles, few works attempt to find risk-sensitive policies. This is surprising for several reasons. First, a moving robot might cause harm to humans, to its environment, or to itself, and risk-averse policies may be safer than risk-neutral policies while avoiding over-conservative behaviours typical of policies based on worst-case analyses. Second, in environments with such complicated structures and dynamics that it's impractical to provide accurate models, policies optimizing risk are appropriate as they actually provide guarantees of robustness to modelling errors. Third, the end users and insurers of robots are risk-sensitive humans, so risk-sensitive policies seem to be the natural choice. If risk sensitivity is so good, how can we make robots behave in a risk-sensitive manner? In RL, one usually looks for a policy that maximizes the average return. To make a risk-averse policy, we can maximize a weighted average, in which we give more weight to bad returns than to good returns. For example, here are histograms showing the return distributions of two alternative policies, A and B. These policies might represent, say, driving fast and driving slower. Now, the red lines show the average returns. The average is higher for policy A, so if we're not risk-averse, we'll pick policy A. However, there's a 1% chance that policy A leads to a nasty crash. Instead, what if we were to ignore the best 80% of returns and take the average of only the lower 20%? This type of average is called the expected shortfall, and insurance companies have used it for decades to compute insurance premiums. The blue lines show the expected shortfall for each policy. Due to the risk of the nasty crash, the expected shortfall of policy A is lower than that of policy B. So, a risk-averse robot would pick policy B, and its behavior would be much safer. The key to most RL algorithms is to keep track of the average return. This works nicely because the average of a sum, usually, equals the sum of the average. Unfortunately, this nice property doesn't hold for the expected shortfall, so existing RL algorithms do not apply. What can we do instead? A decade ago, Morimura from IBM and his co-workers found a beautiful solution to this problem, which they christened Distributional RL. Instead of modelling the average return, they proposed to model the full distribution of the return. As we can approximate the sum of two return distributions, we no longer have a problem. Although it's a powerful idea, it didn't become popular until about 2017, when it was coupled with deep learning. Since then, multiple research groups have proposed improvements to this basic technique. Our own recent work in this domain couples risk-sensitive RL with robot navigation. Surprisingly, it seems to be the first work using distributional RL for navigation in a real robot. Today, commercial robots tend to perform rather specific tasks. If we want robots to perform diverse tasks, then we'll have to find easy ways to explain to them what we want them to do. Well, in the last 20 years, we've made great progress in speech recognition, so surely it should be as simple as telling the robot, "Go and polish the piano keys, but don't make a noise, as it may wake the baby." Yes, human instructions will doubtless be part of the answer, but most of the problem is with getting robots to understand how to do things. And the answer to that will involve a mix of ideas like these. And these ideas are the subject of the next section of this talk. Currently, we get robots to perform diverse tasks using planning and control. For each task, we maximize an objective, subject to some constraints, and a model of contact dynamics. Unfortunately, it can be inconvenient to define an objective and constraints for each task, particularly if there are many diverse tasks to perform. Furthermore, there are big gaps in our ability to model contact, even though both control and reinforcement learning rely on models of contact dynamics. Now, modeling robot dynamics is fine if we only want robots to wave their arms about. Although the equations are complex, efficient algorithms for robot dynamics without contact were developed in the 1990s. However, when a robot performs a useful task, it usually has to touch something, and with touch comes friction. And even though friction's been studied for centuries, when it's combined with robot models, it still raises difficult problems. To illustrate these problems, let's consider a very simple task. There's a rigid rod AB in frictional contact with a curved surface. The task is for the robot to pick up the rod and place it on a table as quickly as possible. Let's model this with classical physics. The first question we would ask is, what happens if we just pull the rod up? It turns out that according to classical physics, the solution is not unique. The rod could remain stuck on the surface for an arbitrary duration until it becomes unstuck. Now, our task was to move the rod as quickly as possible. So to do this, we ought to be able to say how long the rod remains on the surface. But we can't. That duration is undefined. In recent work, some authors think they have a solution to this problem, but as yet, there's no mathematical proof that their solution works. And no existing 3D simulator uses such a solution. But this is just the tip of the iceberg. We face many other problems when simulating contact. Every time there's a collision, there are infinitely many bounces in a finite time. We don't have a way of simulating such bounces that's simultaneously efficient and accurate. Moreover, the real world has effects like elasticity that are not covered by such rigid models. And the behavior of robotic actuators is pretty complex. So, when controlling contact models or training deep learning with contact simulations, we should be aware that lots of work is still needed to overcome these deficiencies. For now, let's ignore that we don't have good contact simulations and boldly forge ahead anyway. How can we get robots to perform diverse tasks without having to define the rewards or objectives manually for every single task? Well, one way is inverse RL. In RL, we're given the reward and must find a policy. In inverse RL, we're given a policy and must find the reward. In other words, we watch someone performing a task and we infer the reward that motivated their actions. But if these rewards are then only used to imitate a human, why go to the trouble of inferring them? Why not construct a policy directly from the demonstrations of the task? This is called imitation learning. Now, imitation learning usually tries to find a classifier that predicts the appropriate actions for the robot to take. Unfortunately, such classifiers tend to require hundreds of examples to do a good job, so by the time we finish demonstrating to such a robot, we could have finished doing the task ourselves. To overcome this data hungriness, 3 special tricks are becoming popular. All 3 tricks exploit the fact that we want to solve not just one, but multiple tasks, and that these tasks have a lot in common. One trick tries to break up tasks into little chunks corresponding to the many ways of grasping, twisting, and turning. We can treat each such chunk as a high-level action consisting of a sequence of low-level actions. In this way, we get a hierarchy of actions. So, this approach is called Hierarchical RL. It helps learn diverse tasks because the high-level actions can be reused across tasks. The second trick, metalearning, is the idea of learning to learn. Now, neural networks learn by making a series of small adjustments to their weights on their way to a solution to the task at hand. So, if the weights start far away from a solution, we'll need to do a lot of learning to ensure good performance. What metalearning does is to find a starting point for our weights that's near the solutions to many different tasks. This way, we won't need a lot of data to fine-tune the weights for a new task. And when metalearning is applied to imitation, it's known as metaimitation. In metaimitation, we train on demonstrations of multiple tasks, and we aim to be good at learning to solve new tasks. The third trick, which we shall call universal policies, tries to find a single policy that can solve multiple tasks when it's given a description of the task at hand as input. One way to use universal policies is to control how we want a robot to perform a task. For instance, when a robot navigates, its behavior should depend on the situation. Cafeteria robots should move carefully to avoid surprising clients with hot coffee, while warehouse robots should deliver packages quickly. In our recent work, we used a universal policy to enable robots to adapt their behavior to specific environments, like the cafeteria shown in this video. Unlike previously proposed methods, ours adapts without needing to retrain the navigation policy multiple times. Moreover, it only needs hundreds rather than thousands of human preferences to discover how humans prefer it to behave. Another type of universal policy takes a demonstration of a task as input. Such a policy is therefore performing imitation learning. But, unlike older imitation learning methods, it doesn't need to train a classifier for each task, so one might guess it needs fewer demonstrations to achieve a given success rate. To be able to test if these tricks really do help robots to learn diverse tasks, we need a benchmark. The first such benchmark, called Metaworld, was released just 1 year ago. It consists of 50 contact-rich tasks ranging from switching on a tap and sweeping to opening a window and closing a door. Metaworld is exciting as it's the first large collection of practical robotics tasks where we can use experience on old tasks to help learn new tasks. So, what if we were to couple together some of the above ideas and apply them to Metaworld? This year, my colleagues have worked hard applying universal policies for imitation to Metaworld. They couple these policies with metalearning by fine-tuning on each new task at runtime, starting from a good initialization. Here are some results showing the success rates on different tasks given 10 demonstrations per task. There's a clear improvement from a 55% success rate to 80% by including metalearning on top of the universal policy. So, while getting robots to perform diverse tasks is an impassioning challenge, currently we can only imitate successfully about 80% of the time, even when we couple several state-of-the-art techniques together. I suspect that there will be rapid progress on this benchmark, and in future, people will design new benchmarks involving different robots with more tasks and more realistic simulations. Since the advent of the so-called transformer model in 2017, there's been rapid progress in the automatic generation of text. One such system from May this year, called Generative Pre-trained Transformer 3, GPT-3, can generate text of such high quality that it can be difficult to distinguish from text written by a human. Such systems work by predicting the next word given the previous words. So to get a system to write such an article, you prompt it by inputting a few sentences. Then, the system generates one word. It appends that word to its input and generates one more word, and so it goes on. As an example, I fed such a model the prompt in blue. It wasn't until 2025 that quantum computers truly started to outperform classical computers, and the system continued. At the moment, there are still numerous barriers preventing quantum computers from achieving true global superintelligence, such as quantum security and quantum concurrency, and so it went on. Okay, it didn't lead us to the greatest invention ever, but it did introduce relevant themes like superintelligence and quantum security. Nevertheless, such automatically generated texts are not yet ready for prime time. Even though they can often pass for human writing, they suffer from many issues. They rely on huge and therefore non-curated training sets, so they often show social bias and sometimes racism and other forms of toxicity. They struggle with consistency, often hallucinating facts. They frequently lose control and lose their own thread, or start repeating themselves. How can we ensure that generated texts remain grounded in facts and include the content that we want them to? Well, several colleagues of mine recently came up with an elegant approach to achieving exactly that. Their neat idea consists in finding a new language model that satisfies some constraints, but doesn't deviate too much from the original pre-trained model. Let's see how this works. Say we wanted to write an article about phasing out coal power. We would begin with a prompt on that topic. However, we knew that there'd just been a major heat wave and most of the article's readers would be in North America, particularly in California. It's difficult to squeeze all that into one small prompt. So, we define 3 classifiers. These identify whether a sentence talks about a heat wave, about North America, or about California. Now, to nudge the generation in the right direction, we impose some constraints. 20% of sentences should allude to a heat wave, 10% to North America, and 5% to California. Now, in the space of all possible language models, the original GPT model is just a point. But the set of models that satisfy our 3 constraints is a surface in that space. What we do is to find the closest model on the surface to the original GPT model. Finally, we generate our text from this constrained model. To prove this really works, my colleague's recent paper contains nearly 20 pages of diverse examples. But to illustrate the idea, let's look at just one really simple example. We will just impose the constraint that all sentences must contain the word WikiLeaks. Now, the best pre-existing approaches to controlling language generation use reinforcement learning. They introduce handcrafted rewards to encourage desirable features and penalize toxicity. However, such approaches often lead to some kind of degeneracy, as shown here. They can get so keen on rewards for the word WikiLeaks that they repeat themselves. The Republican Party has been hacked by WikiLeaks, from WikiLeaks, from of WikiLeaks, from, and so it goes on. But if one reduces the reward just a little, then such approaches completely forget the constraint, and one gets, "There is no way that I can do that, and that's not a small thing," he told The Guardian, where there is no mention of WikiLeaks. On the other hand, our method reliably satisfies the constraints without losing fluency, giving WikiLeaks emails show that Trump campaign was able to hack into email accounts, and WikiLeaks said Monday that a former US official told them that if they'd gone to Moscow, etc., etc. The current system is rather slow, and there's some work to do to define features that can control toxicity and the groundedness of claims, but I think this is a simple and powerful idea that has an interesting future, not just for generating news articles, but also for automatic question answering, translation, and even dialogue interfaces. So, in conclusion, we're pushing the frontiers of AI in 2 domains that are increasingly dependent on GPUs in the cloud. Firstly, we're enabling robots to integrate with our everyday lives by getting them to perform diverse tasks and by designing safe, risk-sensitive policies. Secondly, we're discovering new ways of controlling text generation to ensure coherent and factually grounded results. I hope I've given you plenty of interesting food for thought. Thank you for listening.